So I posted a message to resolve the mix-up. Now you have the PDF version as well as the MLX version. Okay, so I'll quickly walk you through this and then we'll go to quaternions. So this is what I promised earlier. You have a robot, just like when you launched the empty world, it will land here. And I've given you 3 waypoints. You only see 2 here. So the third one is, I want you to bring it back to the original position. Now to bring it back to the original position and have a design heading is a little bit more complicated. So that's why I'm not doing that. I'm just saying, touch a circle around this and a circle around this and then come back here. You can park it any orientation. So just reach and whatever the orientation you get, let's leave it at that. Okay, so here are the details. The initial point is 0, 0, then -2, 4. That seems about right. -2, 4. So actually I do this quite accurately. So waypoint 2 is 3, 2. So 3, 2. And the last waypoint is come back. So it's like a patrol, right? Once you write a program, you can throw in any number of waypoints. You can add yourself and see what happens. You can make it go there and here, and then come back here, and then here. You can give it a tough task. So return to 0, 0. The distance tolerance is 0.2 meters, but you can play with it later. That means a circle of radius, 0.2 meters, not diameter, but 0.2 meters radius. So maybe I should have said radius, but you know what I mean. Yeah. Obviously it can only be radius, because I'm saying if you get within 0.2 meters, yes, you made it. Later you can change it to 0.1. It'll be a little bit more difficult. Then you can make it bigger, and then it'll be a little bit more easy. You can try all that. Now, heading tolerance. It means don't try to go for 0. 2 degrees here or there is enough. All right. So 2 or 3, 2 or 2 plus minus 2 is okay, because nobody can point precisely to a target. It's just cannot happen in the real world. So approximately aim for 2 or plus minus 2. And these programs are going to help you. This is the one we discussed this morning. We spent quite a lot of time. And there is the Euler quaternion conversion program and the heading determination program. So basically you start with OL CL1 and then you do whatever is needed to solve this problem. That original program was doing it as go straight for a certain distance and then turn through an angle. So you're going to have to modify it. You need an outer loop, which is the for loop, in this case for 3 waypoints, right? And then inside you need a test condition while loop to see whether you got within a radius of 0.2 meters. And then within that loop, you got to change the orientation so that it's pointing to the next waypoint. So it's a fun thing to do, It's sometimes frustrating, the path, because it doesn't work initially, but it will finally work. It requires some effort. Alright, so I'm going to shut this down and we're going to start with quaternions. So Sunday afternoon with quaternions, that's the best way to start. So the translation is easy, right? There cannot be any wrapping issue in translation because the scale goes from -infinity to +infinity for each one of the x, y and z directions. So there's no question of wrap. The wrapping issue arises because angles have a finite range. In the case of robotics, -180 to +180. That's why the wrapping issue occurs. For angles, you'll have a wrapping issue because the range is finite. Now, Euler angles, so Euler angles are the 3 angles, and that is the most intuitive way for a human being to assess orientation. But because of a problem known as gimbal lock, we're going to have to move to quaternions. So this is a summary of it's looking ahead and saying, okay, this is why this topic is being discussed, because you have something called gimbal lock, and therefore you have to use quaternions. And the rest of it is the details of the story. This is like a preview, the first slide. So Euler angles, they represent orientation, and the sequence is important. You cannot change the order of the sequence. So you can't do it in any order. It has to be done in a certain order. So a sequence of 3 rotations around the 3 coordinate axis. So here's an example. So this roll pitch yaw, I don't know whether you can see it, but there is a plane there. So these terms are traditional for aircraft. So roll is rotating around the x-axis. Yaw is going like this, rotating around the z-axis, and pitch is forward and back. You know, that's the kind of thing that makes you sick on a boat, the forward and back. So those are the technical terms. As I said, the sequence order has to be maintained. So rotations are quite complicated, as you're going to find out. There can be like 48 axis possibilities. You know, MATLAB can handle all of them if you want to use any one of them, but it defaults to the most common one. The 3 elemental rotations may be extrinsic or intrinsic. Extrinsic means rotations about the axis XYZ of the original coordinate system. So that's fixed axis. That is, no matter if you rotate, everything is with respect to the original axis system. Or, which is more useful, it can be intrinsic rotations about the axis of the rotating coordinate system. This is more natural because when the plane rolls, you want to take the axis with you and not still refer to the original axis. So that's from Wikipedia. There's probably a more scientific definition somewhere. Please come in. We're going to get 12 orderings. We're beginning with there's many more. So, since it is 3 angles in a proper sequence, what are all the possibilities? Now, you can have XYZ. In other words, let's first go without repeating the axis. See here, you get repeated axis and you're going to say, hey, we left out Z. I'll tell you why you're not leaving out anything shortly. So here we're going with all the axes except that it's an order, X, Y, Z, Y, Z, X. So you get how many possibilities? You get all of them. X, Y, Z, Y, Z, X, Z, X, Y, X, Z, Y, Z, Y, X, and Y, X, Z, right? 1, 2, 3, 4, 5, 6. But you can also repeat the axes. Why is that? Because when you move, the new X is not the same as the old X. Got it?
Yeah.
So X at the end here does not mean the same thing as the X at the beginning. So therefore you're not losing any freedom. You don't have to have Z involved. It can be an XYZ, XYX, or a YZY, or a ZYZ, XZX, and YXY. They've gone through all the possibilities. You cannot have an XX together, because if you have an XX, then the question will be, why don't you just combine the 2 X's, right? So X and X together without a sandwich. You know what I mean by a sandwich? There has to be something else in the middle. You can't have XXY because it would make no sense. Then the 2 X's are the same, and you won't be able to cover all orientations because XX is basically X. So that's why you end up with only these possibilities. You cannot repeat in sequence. You have to separate them in a sandwich. See? Separated in a sandwich. So you get non-repeated as well as repeated axis. Repeated, non-repeated. Got it? Also, repeated axis must be separated in a sandwich. So total of 12 cases, right? But now you take the moving axis and the fixed axis and double them, and you end up at 24. It can get very confusing, except that we lay down a convention and we follow it. You know, when we are working on a robotics problem, we don't switch in the middle. You know, it would be foolish to do that. So everybody who's working in this team has to use this convention. So MATLAB default is yaw pitch roll, that is ZYX. This is the MATLAB default, but you can't change it. You have to put like a different sequence, you know, in codes, and it switches to the new system. I'm sure it's the same thing in Python, working on robotics. There must be libraries that do that. So, is the MATLAB default intrinsic or extrinsic? No, it's intrinsic. You can also get extrinsic in MATLAB, but typically it's intrinsic and ZYX. So, you know, this is not a mathematics class, but sometimes in engineering, you just are interested in something, even though it's not going to produce a salary. So if you really want to understand these rotations, it's like a massive effort. And the way to do that is to do rotations in MATLAB using a non-symmetric 3D object. Because if you use a cube and you rotate it, you won't know what happened. So typically take dice, you know dice?
Yeah.
It has numbers on all the faces, so you can figure out exactly what happened. Is it what you think it should be, or is your understanding, falling short? So you either use an unsymmetric object, or you use dice with numbers on the faces. So Euler angles, what is the advantage of using the Euler angle system? It's simple and intuitive and easy to visualize. So that's the beauty of it, right? There's only 3 numbers for 3 degrees of freedom. Quaternions is going to be 4, x, y, z, w. But it's going to avoid gimbal lock, so worth it. So gimbal lock, you see, is a major problem. Also, when you work with Euler angles, and I told you this, in gaming, you have this situation where you're trying to create video sequences, right? All these cartoons and all that, right?
Yeah.
So gaming, you don't have an actor doing this and you take a picture, a video. You do this by the computer is generating the sequence, somebody's fighting the sword, so the computer is generating this entire thing, like transforming the arm, right?
True.
So that involves interpolation, because you have an initial position and a target position, and you got to fill in all the intermediate values by interpolation. If you interpolate with Euler angles, it is not uniform motion. It might go like this, because the angles don't map, they're not a linear mapping to motion. Quaternions is. So when they defined quaternions, they found out that it's smooth. The quaternions allow easier interpolation. So I told you, the older gamers, they figured out, okay, let's not space the angles out evenly, let's compensate for it by, they knew what angles to use in order to compensate for it. They have a library, they call it up, and they get smooth motion. Too much work though, but if you've already done it, then it's not work. It's more work learning quaternions, right? So that's what they were thinking. The older guys don't change that easily. So the key problem is that the mapping from spatial orientations to Euler angles is discontinuous. Small changes in orientation cause big jumps in the required representation. Okay, and you can go to this, it actually explains that phenomenon. But the bigger problem is the gimbal lock. So we're going to watch this, okay? Let's watch that. Look at this.
It's okay. It's nothing to be ashamed of. It happens to everybody at some point. It's perfectly natural. I'm talking about gimbal lock, of course. I'm not sure what you have in mind. So if you don't know what a gimbal is, today is your lucky day, because I'm about to tell you. A gimbal is a suspended support that can rotate around an axis. Most commonly, it's a ring. This Euler gimbal is the one that you're probably most familiar with if you're in the 3D animation realm, which we use for rotating objects and has gimbals nested inside one another, and a particular hierarchy. Each ring can pivot around an axis, so that the entire gimbal system can rotate on multiple axes. Gimbal lock is when 2 of these rings have been rotated in such a way that they both align and start to rotate along the same axis. So in 3D animation, that means some whack shit is bound to happen in your rotations and interpolations, because the software is trying to interpret how to get around the issue. The thing is that it's really important for you as the animator, or as the rigger, to pay attention to the hierarchy of the rotation order of these gimbals to avoid the dreaded gimbal lock. The hierarchy is that the outermost ring is the parent, the middle ring is the outer ring's child, and the innermost ring is the child of the middle ring.
So you know what that means? The outermost ring will rotate all the other interior rings. It's a parent. But the interior one will not rotate its parent.
Yeah.
Right? So the middle ring will only rotate its child, but not its parent. And you'll see how the gimbal lock is caused because of the system.
So you see that the innermost ring can rotate independently, but is also affected by the rotations of the 2 outer rings. The middle ring, when rotated, will also rotate the innermost ring. And the outer ring, when rotated, will rotate all 3 rings. Now, you might be wondering where Euler rotation comes into all of this. This dude, Leonhard Euler, was a mathematician, physicist, astronomer, all-round overachiever. I mean genius. And he figured out this rotation theorem, which is that when you have a rotation system in 3D space, it has these axes, the X, Y, and Z axes that rotate around a fixed origin point. So the gimbal is the axis system used for performing Euler rotations, and hence why this is an Euler gimbal. Now there are different Euler rotation modes in your gimbal which depend on the hierarchy I mentioned earlier. We have 6 possible modes or hierarchy combinations according to the axes we have to work with.
We actually have more than
X,
6.
Y, Z, X, Z, Y, Y, X, Z, Y, Z, X,
So no repeated
Z, X,
axes,
Y,
that's
and
why.
Z, Y, X Euler rotation modes. These are named for the axes in order of the hierarchy they're in, starting at the bottom of the hierarchy and ending with the axis that's at the top of the hierarchy. So for example, in this one, X, Z, Y, X is at the bottom of the hierarchy, Z is in the middle, and Y is at the top of the hierarchy. The big cheese of the axes in this rotation order. You can see how easily you can get into the situation of gimbal lock. So I have this rotation manipulator here, right? And I'm going to change the transform orientations from local to gimbal. You might wonder why I don't just leave it at local, since when I'm in local and I rotate the manipulator, the X, Y, and Z axes seem to stay equidistant, so it stands to reason I wouldn't experience gimbal lock, right? Unfortunately, that is just a visual representation, and the software still calculates with Euler rotations. So gimbal lock would still occur. So it's better to have it set to gimbal so you can actually see what is really going on. So I change it to gimbal so that it'll get an accurate representation of the axes. And if I go to my object properties, I can see that it's set to X, Y, Z Euler. So X is at the bottom of the hierarchy, it's parented to Y, and Y is parented to Z. Z is at the top of the hierarchy. If I grab Y, the green one, which is the middle axis here in this gimbal that's set to X, Y, Z Euler, and rotate it, you can see straight away I've become gimbal locked because X is a child of Y. So when I rotated Y, X rotated as well. And now X and Z are aligned and rotated.
So you know what that means? If X and Z are aligned, how are you going to get 3 degrees of freedom?
Yeah.
Because 2 of them are saying the same thing. So what would happen with the transformation matrices we discussed this morning, it's not going to be able to transform it because there's not enough information, right?
Yeah.
So that manifests itself by blowing up. You get infinity. Suddenly in the transformation you'll generate numbers that are infinity. And obviously you can't proceed beyond that. They had this problem on Apollo 13. You can Google it. Apollo 13 gimbal lock. And they solved it on the fly. They were already on the way to the moon. So they managed to solve it because it's a big problem.
On the same axis. So we've now lost the ability to use one of those axes, and I'm basically stuck with 2 now, because these 2 are rotating on the same axis. So if I was doing that to a character's arm and keyframed it there, my 3D software, Blender in this case, would try to figure out what the hell I did and fix it for me with some weird interpolation. So now we hopefully understand what gimbal lock is, but how do we fix it? Or even better, avoid it? Because prevention is better than cure. Well, gimbal lock occurs in any Euler rotation system, no matter what the parenting hierarchy is, whether it's X, Y, Z, Z, X, Y, Y, Z, X, or any of the other possible combinations. Because of the parenting, when you rotate the middle ring, whichever is the middle of the hierarchy, to 90 degrees, the lock is going to happen. So we need to be deliberate in what rotation order we decide to use when animating. If the middle axis in the rotation order is what causes gimbal lock when it rotates to either negative or positive 90 degrees, then we need to try and make sure that whatever rotation order we're using would use that axis the least. And that if we do need to use it, it won't need to be rotated to 90 degrees.
That's the point. So that the middle axis, you got to prevent it from ever getting to 90 degrees. So that's what I was saying. The camera, if the camera is mounted on the middle axis, that could be trouble. But typically cameras are not pointed way up, right? You may stop here and you may stop here. So then you're okay. You're never going to encounter it and you're fine with transformation matrices. You never have to even think about quaternions. But otherwise you have to.
So let's look at it this way. We have this gimbal, and instead of using X, Y, and Z as our axes here, because it depends on the rotation order, and you could be using any rotation order, let's rather use A, B, and C, because those letters can apply to whichever axis you want.
I think we got the idea. We don't need to go through the rest of it. You can be watching on your own. So that's another gimbal lock description. There are many of them on the internet. So of course, the pitch angle is plus minus 90 degrees for the system of 2, which is the system described in this reference here. Then you get only 2 numbers you get two numbers representing the same thing. So you get a loss of degree of freedom. Both yaw and pitch represent the same rotation, and the matrix will blow up. So I mentioned this, plus minus 90 degrees is when you're going to have the problem. So by the way, when you get close to plus minus 90, the numbers will already start to get big and big. So you can't go to 89 because the computer might find even those numbers difficult to handle. So you may have to stop at 70 degrees or 75, but that's okay for a camera, you know. You don't really need to point it up, you know, this way. It depends on the application, of course. If there's you're watching an air show, maybe the plane is going here and you want the camera to go up here. So it depends on the application, but typically you need to keep it out of plus minus 90 or even close to it. Okay, so this system, right, is different from Euler angles. It is the stepping stone to quaternions. So it's called axis angle, right? So, I'm sorry, this color coding you already know. Skip this. This is what I was talking about. This is the stepping stone to the quaternion system. It's called the axis angle representation. And what it is it's based on something that Euler came up with. Euler's rotation theorem. He was doing a lot of things, you know. That was the practice those days. Newton was a physicist as well as a mathematician and an inventor and so many other things. There were no well-defined disciplines in those days, you know. People did anything that they could. So this method, axis angle, is like the cousin of quaternions. It represents orientation with a unit vector plus scalar combination. The scalar is the amount of rotation. So Euler showed through his rotation theorem that if you have a plane like this and you want it to end up in this position, there is one axis that you can find. There's a way of finding it. You know what I'm saying?
Yeah.
It's not three consecutive rotations as in Euler. He found out that if that has to become this, there is one axis and one angle. If you take this and find that axis and rotate about this angle, you'll end up in the new position. So that's what the Euler rotation theorem, you know, figured out. Okay? All right. Now, the scalar is the actual amount of rotation. It has both positive and negative sign possibilities. So positive would be one way, negative would be the other way. It has to be a unit vector in this system. A unit vector just means that square root of kx squared plus ky squared plus kz squared is equal to 1. So I don't know whether you took a class on vector algebra,
yes.
But essentially if you have a unit vector, kx squared plus ky squared plus kz squared square root of is equal to 1. Okay, so that's this axis angle system. Now we move to quaternions, which is the cousin, which looks very similar. So what we're going to focus on is how quaternions can be used to implement coordinate transformations. We are not interested in the background theory, because if I did the background theory, you would probably be here all night. You know, it's quite complicated. And you know why? Let me tell you the story. So there are 6 videos. Reference 3, if you look at the last page, 6 YouTube videos. So about 7 or 8 years ago, I spent a hot summer in Chennai watching these 6 videos. Actually the first 5 are the most useful, the 6 is not that useful. Over and over again and trying to take notes. You know how it is. You stop it and you rewind it and then you take notes. So that's when I first learned quaternions about 7 or 8 years ago. And it takes multiple viewings. You have to go through it. I did that all summer. And a lot of math. And if you let a couple of days go by, then you've forgotten everything. Now you got to go back and watch it from the beginning. So basically, that's the mathematics. It's quite complicated. So we're not going to worry about how they came up with this. We're going to worry about how we can use it. That's all we're interested in. So focus of discussion is how quaternions can be used to implement coordinate transformations. No coverage of why. You can go read that on your own or watch those YouTube videos. That was 7 years ago. Maybe they have better YouTube videos now. But the backstory is very interesting story. So complex numbers can be used to represent a point on a plane, right?
Yeah.
So 3 plus j4 can represent the point 3 along the real axis and 4 along the imaginary axis. So he was looking for something equivalent to that in 3 dimensions. So he wanted something the equivalent of complex numbers for a single plane in 3 dimensions. So that he can represent points in 3-dimensional space. One thing, this new number system that he was trying to create, so any new number system has to follow a set of rules. The operations within that have to satisfy some rules. What he was missing was how to do multiplication and division. He couldn't figure it out for a long time. And because of that, he could not finalize it. So he had everything, but he could not define the mathematics of quaternion representation. Just like complex math, there's a whole bunch of rules, right?
Yeah.
He was trying to do the same for quaternions, but he could not. He could not figure out how to calculate division of the coordinates of 2 points in space. And then this happened. So this is a famous bridge in Dublin, Ireland. So is there a plaque here? So this plaque is somewhere on the side here. It's blown up here. Here, as he walked by on the 16th of October, 1843, Sir William Rowan, Hamilton, I guess, in a flash of genius, discovered the whatever. Yeah, I can read it, but
Formula for quaternion multiplication.
yeah, right. So apparently, the story goes that he was walking with his wife, and they were, chatting, and then all of a sudden he became silent. He was not responding to what she was saying, and at that moment, he figured out how to define multiplication and division. And so quaternions were discovered, and from that point onwards, they made our lives miserable because he introduced it to the whole world. So this is a famous bridge. If you ever go to Dublin, Ireland, you should visit this bridge because the plaque is on the side somewhere here. You can see it's a bit weathered. He was one of the greatest mathematicians of all time, Hamilton. So it's a convenient mathematical notation for representing 3D orientation. It's not easy to interpret exactly what does it mean. We don't know, we know how to use it. But if you watch those videos, you'll know what it means. The underlying mathematics leading to definition and use is not easy to understand, even as one can learn how to use them. Gibbon-Lock problems are eliminated, and there is numerical stability. Remember I told you, when you get close to Gibbon-Lock, the matrix approach of transformation will blow up. All the numbers will start growing up. Here it has numerical stability compared to rotation matrices. With the Euler angles, and it's more efficient than using the rotation matrices because the rotation matrices turn out to be these 4 numbers, right? It's the entire matrix, right? And it's a lot of numbers. It's 3 angles, but the rotation matrix is 3 by 3, which is 9 numbers. Here it is just 4 numbers. So 3 is the minimum.
Yeah.
3 degrees of freedom, you need 3 numbers. Quaternions uses 1 more. The rotation matrix has a 3 by 3 to actually implement it. So, and you get smooth motion interpolation. So that's the reference. So let's see what it is. So it's a set of 4 numbers used to represent rotations, and it is in this order. Now I noticed that ROS has it backwards. They use the vector first and then the W, whereas MATLAB uses W first and the vector next. This is going to be a vector, by the way, similar to the axis angle approach, but they list, one of them listed the other way around, ABCW, and in December I was trying to prepare some programs for the course, and the robot was falling over. When I tried to move it to a new location, it was lying on its side. I could not figure it out, and finally I noticed that it was WABC in MATLAB and ABCW in the other system. So I had to take the numbers and repack it for use. And then it worked. So here are the numbers. So W is cosine 0.5 theta. So this is the amount of rotation around the axis defined by ABC. Is that clear?
Yeah.
ABC is not required to be a unit vector. In the other system it is. Here it is not. So ABC is the vector. W, the angle is buried in it. It's not just the angle, right? It's cosine of half of the angle. Now, why half of the angle? Why not the whole angle? Go and watch the 6 YouTube videos. It's very dense, the whole theory. But over here, you have cosine of 0.5 theta. So therefore, if you want to rotate by 90 degrees, this morning we tried to rotate by 90 degrees, right? Because some of the examples in Jennifer K's lecture notes was 90 degrees, then what you're going to have to do is, you're going to have to put 90 here, and half of that and take the cosine. So the angle of rotation is buried here, indirectly.
Yeah.
But look at this. So sine 0.5 theta, same thing. Sine 0.5 theta, sine 0.5 theta, sine 0.5 theta. That does not change the orientation of the vector, right? It's occurring in all three elements of the vector. Do you see that?
Yeah.
So it's going to cancel out. So basically Vx, Vy, Vz is the vector. They just add on. For the quaternion, you have to multiply by sine 0.5 theta, sine 0.5 theta, sine 0.5 theta. So quaternion structure has similarities to axis angle parameters. Axis angle information is indirectly present. ABC reflect rotation axis information within a constant, right? Within a constant, see? ABC, it's got the rotation angle instant, but except that there's an extra constant here. And finally, omega is directly related to the amount of rotation, because theta can be obtained as cosine inverse of W, because this is W, times 2. Because the 0.5 becomes 2 on the other side. So you can, so when they are doing an Euler to quaternion conversion, nothing great, because basically, something simple like this, but they are avoiding you having to put in the formula, right? MATLAB function gives you the result, but essentially the angle can be peeled off from W like this. Okay, now a little bit into the math, not too much, but a little bit. So it's basically the quaternion, what we write in short form as WABC. The quaternion itself is like a regular complex number, except that it's an extension of the complex number. So Q is W plus AI plus BJ plus CK. So now we have IJK. In the traditional complex number system, we only have the I. We don't call it I in electrical engineering, because I can also be current.
Yeah.
We call it J, right? So Q is equal to W plus AI plus BJ plus CK. And these are the rules of multiplication. I squared is equal to J squared is equal to, Hamilton came up with all of this, including the missing piece. Multiplication is here, right? I squared is equal to J squared, multiplication is involved here. It's equal to IJK is equal to -1. And similarly, he's got a whole bunch of things. Ij is equal to K, Jk is equal to I, blah, blah, blah. We won't go into the details of this. But that's what he came up with. So essentially, the quaternion is defined, by the 4 numbers. Complex numbers is comparing, he's comparing complex numbers with quaternions. What is the difference? So in complex numbers, you have I squared is equal to -1. Here, you have 4 of them. I squared is equal to J squared is equal to K squared is equal to IJK is equal to -1. So just a quick comparison between complex numbers versus quaternions. This is the definition for complex numbers, this is the definition for quaternions. We'll soon get to use it. That's where we want to be. So this is the complex conjugate of the quaternion. Remember the complex conjugate of a complex number?
Yeah.
So the complex conjugate of a quaternion is W, and you put a minus sign, for all the other elements. And you know what that means? This represents the vector, right? This is the axis around which you rotate. So if you flip the signs, it means the axis is being reversed. Right? So that's what is happening. Instead of rotating around this, you're rotating around this. Now remember, theta still remains the same.
Yeah.
But if the axis changes, then you're rotating in the opposite direction now. Because the same theta over an axis that is flipped this way means the opposite rotation. Right? Theta is still the same, it hasn't changed. We're not flipping this. Theta is here, right? Theta is here. We're only flipping the axis. So it's like rotating in the opposite direction. Okay, then the norm of quaternion, that's like the, what do you say for complex numbers? It's the magnitude of the complex number. X plus jy, square root of x squared plus y squared, remember that? So similar to that, for the quaternion, we have the norm of the quaternion in the square root of q multiplied by its conjugate. Is the same as the opposite, square root of q star, q conjugate times q. And it can be shown to be this.
Yeah.
So square root of first number of the quaternion squared, second number squared, third number squared, fourth number squared. Now, if you want to know how to do this, first you need to know what is the multiplication operation. That is defined on slide 17 coming up soon. You can actually prove this. That the norm of q, which is the square root of this or square root of this, is actually this. You don't have to take for granted. You can actually multiply it out, provided somebody tells you how to multiply it, and that's coming soon. Let's go to that first. So, how do you multiply these two? How would you multiply two complex numbers, right? How would you multiply x plus y times L plus Q? You'll go x times L, right? You know what I'm talking about? A plus B times C plus D will be AC plus AD. You'll have 4 terms, right? That's exactly what it is. He's taking this because, that's a compact way of representing it. The real form is right here. Here, this is the form. So if you write Q and next to it you put Q conjugate, which is all these signs flipped over, and if somebody defines multiplication, well, anybody can do it. It's logical because all you have to do is go W1 to W2, right? But remember, the A1, B1, C1s have an IJK attached. So when you multiply this and this, you'll also get an I squared. But we just now defined rules for how to deal with I squared, right? Here it is, I squared is equal to J squared is equal to K squared is equal to -1. So if you use that to clean up, and you don't have to do it now, you can go home and do it if you're curious, you will end up with another quaternion whose first W, the equivalent of W for Q and Q2 is all of this. The equivalent of A for the product is all of this. Got it? The equivalent of B for the product is all of this. And the equivalent for C is all of this. And quite simply, you take it and multiply, use the rules, these rules, and you can get it. But all that is fine. We want to know how it will help us in robotics. So we're getting to that shortly. Alright, this is the slide that we missed because we jumped ahead here. But if you have a unit quaternion, the norm is 1. What is the norm? We just defined it. Here it is. So for a unit quaternion, the norm will be 1. So W squared plus A squared plus B squared plus C squared square root of will be 1. And then he also shows that the inverse of a quaternion, for the unit quaternion, the norm, the conjugate is the same as the inverse. So the inverse is defined like this, and the inverse will be the same as the conjugate if you have a unit quaternion. What is the unit quaternion? It is something that has this equal to 1. That's a unit quaternion. And for that special quaternion, you'll find that the inverse and the conjugate are the same thing. I'm kind of rushing through this because what's the point? We want to get to the robotics part. Okay, now, multiplication between two quaternions is not switchable. You cannot switch it. Q1, Q2 is not the same as Q2, Q1. This is similar to matrices. AB is not equal to BA. First of all, AB and BA, they have to have a relationship between the rows and columns. Otherwise, you cannot even multiply them. But even if you could, AB is not equal to BA in matrix theory, right? Similarly, when you multiply Q1 by Q2, pre-multiply Q2 by Q1, it's not the same as pre-multiplying Q1 by Q2. Okay, this is the main page. And then we're going to try it out in MATLAB. So, what does all this mean in terms of, rotations? So, assume that VL is a vector in the local frame of reference. VW is a vector in the global or world frame of reference, right? And QLW is a quaternion representing transformation from the local to the world. See, local to world. So VL is the local frame, VW is in the world frame, and QLW represents a quaternion. We're going to see how to build that, right? Shortly. So QLW is the quaternion to move from the local frame to the world frame. Then look at this. If you create this sandwich, so you want to transform from the local frame to the world frame. So you take the vector and make a quaternion of it. How? Because a vector is only 3 numbers, right? But a quaternion is 4. So this is how we do it. We add a 0 to the first element and leave the vector as the bottom 3 elements, right? So you get 4 numbers here, right? So you take a vector, add a 0 to it, like pad it with the 0 there, it becomes a quaternion, and then pre-multiply by QLW, which represents transformation, rotation from local to world frame. This one, QLW, inverse. See, this is a quaternion with norm 1. So conjugate is the same as inverse. And if you do that, you end up with a quaternion. And the quaternion will end up with a 0 in the first position. You unpack the bottom, and that will be the vector in the world frame. So this is a complicated series of operations, so I'm going to repeat it. You take the vector you want to transform into the world frame, locate the world frame, add a 0, make it a quaternion. 3 multiply by the quaternion representing transformation from local to world frame. Post multiply by its conjugate, which if you have a unit quaternion is the same as the inverse, and you will get a resultant quaternion, the bottom 3 elements of which will be the transformed vector. We're not going to take it for granted, we're actually going to do it. Why? Go watch the YouTube video. So this is just the result. Finally, after 5 videos, he gets to this, he says, okay, this is how it is. Alright, so the sandwich is this one. This is the sandwich, right? You put the initial vector here in the middle and sandwich it with 2 quaternions. So that's why it's just, you need a sandwich operation. You need 2 quaternion multiplications, this with this, and the resultant with this. So 2 quaternion multiplications. So those are not regular multiplications. Remember, this is quaternion multiplications. What is quaternion multiplications? Here it is. Hamilton. This is known as the Hamilton product. The Hamilton multiplication in honor of Hamilton. So that's what they mean. So do quaternion multiplications. Don't do any multiplications. You fancy. And finally, before we go to the MATLAB program, what would this mean then? Suppose you create Q, where Q2 represents, let's say, camera frame to robot frame. So maybe this is camera frame to robot frame, right? And then Q1 represents robot frame to world frame. You got it? So Q2 is camera frame to robot frame, and Q1 is robot frame to world frame. If you do this, then it represents camera frame to world frame. So you have to do it in pieces. There is a quaternion for each segment. So you can take it from your camera to your robot frame to the world frame, and then you can take it to the second robot's coordinate frame, and maybe to its LiDAR, whatever you want to do. So that's how you go. You go to the world frame and then you come back to all the other frames. Just put together the sequence, and then finally you will have a vector. You know what to do with the vector, it has to be sandwiched, and then you're in business. Okay, so this is answered, this question is answered in MATLAB. So let's open up MATLAB and make sure that we have the right program today. This morning I did not. So it is an MLX file. I think it is HT1, but I could be wrong. Let me see. Is there a program already uploaded to Teams, which is called HT1 perhaps? But this is only for, am I doing quaternions here? I don't think so. Yeah, with quaternions, yeah, right there, it says with quaternions. I typically put a lot of comments in. Okay, yeah. So I made up this problem. So there is no translation between these frames, okay? Translation will be handled exactly how you handled it before. Quaternions are for rotations only. So numerical example illustrating how to employ a quaternion to carry out transformation of vector from one frame to another. Here a pure frame rotation is executed. If translations are involved, they can be handled in the regular fashion and after frame alignment. You first have to align the frames, right? We said that before. You can't do translation unless you align the frames. So here it is. Look at it. Not the greatest of drawings, but that's what I came up with in short order. So here's the world frame, x-axis. So that's the red axis, green axis, and blue axis. And I have a point there, or in other words, the vector 0, 0, minus 1, 0 along x, 0 along y, and it's dipping down to minus 1. And I want to find what it is in the local frame, right? I know the answer, right? It's got to be 1 along the x-axis, right? And 0 along the others. I can make up any number of problems like this, right? I said that this morning. So long as the rotation is 90 degrees, you can make up any number of problems. Okay, so I'm transforming from which frame to which frame? Use quaternion to transform a vector from local axis to world axis. So I'm going this way. So I define a vector in the local frame, 1, 0, 0. See, 1, 0, 0. So this is where the problem originated. I was talking as if it's the other way around. This is given first. And then you say, okay, that's got to be the answer. Got it? I said it the other way around. So because we're transforming from here to here, that's what was present at the beginning. So V local is 1, 0, 0 transpose, right? Enhance it to quaternion form. See what I did here? I added a 0 and then I put V local transpose. So then it becomes a vector. Define quaternion representing relationship between frames. So I was trying out different things. Now, how did I get this? 1 over square root of 2, 0, 1 over square root of 2. So I'm going to give you a few minutes. Remember the cosine 0.5 theta? And then sine 0.5 theta was there in all three, right? So go ahead and do that. Calculate the cosine 0.5 theta. 90 degrees, what is 0.5 of that? 45 degrees? So 1 over square root of 2. And what is the rotation? Hey, how do I rotate this to back to this, right? So y is going this way, but it needs to label this. Z is going upward. So Z is aligned with X. I missed a label here, or is it hiding somewhere? Yeah, there it is. So Y and Y are already aligned. X and Z. Rotate. Who said? Huh? Rotate around.
-9.
Yeah, right. -90 because of the right hand rule.
Yes.
Yeah. So I want you to make sure that this is right. What is this? So that is the numbers showing you the axis around which you're going to rotate. Remember axis angle? It's the same thing. You have to find an axis to rotate around and the amount of angle, right? Except the angle is not the first number. It is cosine 0.5 theta of that angle. That's why you get 1 over square root of 2 here. Right? And the axis isn't this a y-axis? Why did I put 1 over square root of 2? I think I tried to make it like unit quaternion. You know what a unit quaternion is?
Yeah.
Square root of this squared plus this squared plus this squared plus this squared should be equal to 1. That's what a unit quaternion is. Square root of every one of those elements squared. So isn't square of 1 over square root of 2 is half? 1 over square root of 2 is half? So half plus half is 1, right?
Yes, sir.
So I'm following the rules. I'm trying to create a unit quaternion. That doesn't change the fact that this is still the y-axis. I could have put any number here. I could have put 10,000. It would still be the y-axis, right? But I try to make it a unit quaternion. That's all. Now, the conjugate of the quaternion. You know the conjugate? Because, I closed that down. But if you look in your notes, you have a q here, another q here. And the vector is in the middle. It's a sandwich. The q here is the conjugate or also the inverse if it's a unit quaternion, right?
Yeah.
So that's what I'm doing here. Define the conjugate of the quaternion. Flip sign of vector. So 0, 1 over square root of 0, here is 0 minus 1 over square root of 0. In other words, I'm not doing anything great. I'm just doing what I found out from the YouTube video. So I take this and pre-multiply by QLW and post-multiply by QLW conjugate. But if you have a unit quaternion, QLW conjugate is the same as QLW minus 1. That's all I'm doing. I'm just implementing it blindly. Is it okay? Everybody got it?
Yeah.
Because you're going to do something. You're going to take the result and move it back to the origin, just like we did this morning.
Yeah.
We're going to apply the reverse quaternion, transformation. Now, the Hamilton product is available in MATLAB. It's available in the aerospace toolbox, and nowadays the license covers all the toolboxes, but you may not have downloaded all the toolboxes. And I was just curious if I could write it myself, so I created a function. Here, I wrote my own function. If you can't access the MATLAB function, I already did.
Yeah.
So you have it with you, right? You have the whole code. So I'm doing it locally because I just wanted to see whether I understood, how to put, see this is not, I just copied that. Remember the product was given as W, A, B, C for the product, I just copied it down. So I'm just unpacking, see I'm entering the two quaternions to be multiplied and I'm unpacking them. Because I like my code to be clean. I don't care if I'm using more memory. I like it to be clean so that if I come back 6 months later, I can figure out what I did. So I pull out W1 from Q1 1, Q1 2 is A1, B1. I like it to be like that, and then I multiply it out. So it's not much, but MATLAB does it automatically. Everything is hidden to you. You don't know what's going on inside. If you like that, go with the MATLAB function. Okay, so define the conjugate. Carry it out. So here it is, QV int. So int is just the intermediate result, because remember I have to pre-multiply and then the result has to be multiplied again. So I call this the intermediate result. My QMult, that is the function, I send in Q and QV local. The intermediate value is just the first multiplication. Then I take that result and pass it again into the multiplication function. And this time it is QV int and Q inverse, INV. Originally I had Q, right? I also defined a Q INV here. And do I get the right result? So what should you do with this number? Ignore it. Because the result is a quaternion and the 0 has to be thrown away. So the answer is 0, 0, minus 1, right? Is it correct? 0, 0, minus 1. So there's no round off error even. See, you get a perfect 0 at the first part. Maybe in other cases you won't, but here you do. You get a perfect 0. And you throw that away. And the remaining part is the vector. Now, I want you to take that vector and reverse rotate it. So see what you need to do to change it. You will have to define your two Q's. It's not difficult, because if you transform one way to transform the other way, you flip the sign of the last three. And then you'll have to create its inverse and then run it through the multiplication function twice. And hopefully you'll end up with this answer, which is right here, this answer. You need to get back 100.